Okay, welcome back to Chemistry 2330. We're going to continue on with Chapter 9 today. For Chapters 10 and 11, that's amines and spectroscopy, I'll be using my goals slide that are found on Canvas and on uh, Top Hat so that we can get caught up and make sure we get a little bit of our review in and have our upcoming exam happen on the same day. So let's go ahead and continue with that. I'm going to go ahead and share my screen. And we're going to continue on with the Chapter 9 lecture. If you did go ahead and look at the videos online, you'll see that it's the exact same slides, and it's just, I've recorded them probably about a year ago, and so it should be all the same information, and so that you can get there. And again, if I go too fast on my explanations here, you can always go back to those and look at those again. Okay, so the cool thing about Chapter 9, the cool thing about benzenes is the only reaction we have is called electrophilic aromatic substitution, and they all have the exact same mechanism. The tricky part is figuring out how you're going to make that electrophile, that thing with the positive charge. Okay, so in all of the reactions we're going to do is we're going to create that positive charge. Once that positive charge is created, the benzene ring acts as a nucleophile and uses the electrons from that benzene cloud to reach out and grab that electrophile and create a new sigma bond. When it does that, it creates a positive charge. That positive charge is stabilized around the ring, and so that we will need to pay attention to this positive charge here. Okay, so we have this positive charge moving around the ring that stabilizes it here, but of course, it has that driving force to aromatize. It has that energy saved when it aromatizes. So the easiest way to lose a positive charge is to kick out a hydrogen and use those electrons to give us our third step, which is our elimination of OH. And it happens with any base, any Lewis base that has a lone pair there can act as that base and re-aromatize the ring. Because again, the ring wants to really be aromatized, and so that is always a fast step. Now, pay attention to the fact that we have this moving around. This plays a critical role in whether or not where the attack is going to happen once we have a substituent on the ring. And we'll talk about that today. Okay, so I did talk about bromination and chlorination. And in both cases, we're using a Lewis acid catalyst to generate that chloride positive charge, the chloronium ion. Okay, so we have a positive charge on chlorine, and that is now our electrophile. That's the hard part. We have to do that. That's our slow step. Once we have that, the the benzene will reach out, and this is our actual rate determining step, because this has to happen before anything else can happen. You can form that chlorinium, and then it can break back and form again. But the slow step here, the necessary slow step, is this one right here. 2 electrons from the benzene ring reach out to create a new sigma bond. In that, it creates a positive charge on that ring, and that moves around the ring until we lose the hydrogen and re-aromatize. Okay, so that means whenever we have the chlorine on that ferric chloride Lewis acid catalyst, oh, sorry, then the iron tetrachloride here can act as a base and remove that proton, giving us our final product and an acid, and regenerating our FeCl3. Notice we're regenerating that ferric chloride. So that's why it's catalytic, and then it can go react with another molecule of chlorine to keep the process going. The same is for bromine, except we would want to use iron tetrabromide, because we don't know which of these halogens is going to leave when we form that cation. So we would want to use the iron tetrachloride for chlorination and iron tetrabromide for bromination. So we saw that we could do put a bromine or chlorine on there, or a nitro group, or sometimes a sulfur group. Okay, so but the first step is the same. We have to create something with a positive charge. Okay, so that something with the positive charge we're going to generate is called No2 plus. And the way we generate that is we take our nitric acid right here. So this is our our standard H2 HNO3 right here. And we've drawn it out so we have an OH on there so we can show you where that it is going to be protonated. We use the lone pair on one of these oxygens to protonate it. And then this leaves, the water leaves, generating the nitronium ion. Okay, notice we're using sulfuric acid as the protonating species. And when water leaves, we have that nitronium cation. Okay, so now we have our cation. So now once we have our cation, it can then be attacked by the benzene ring and again lose water, and that's how we get a nitration. So for chlorine and bromine, we have iron tetrachloride. For nitration, we have nitric acid and sulfuric acid. Okay, so again, same mechanism each and every time. The next thing we can do, we have two other reactions, and they also use catalysts to create a positive charge. In those two other ones, though, instead of forming a chlorine carbon bond or a nitrogen carbon bond, we're going to form a carbon bond. We have two different types of those. The first one is what we call Friedel-Crafts alkylation. Notice it says alkylation. Okay, so that means we're going to be putting on a some kind of alkyl chain or something like that. So we're going to have a carbon-carbon bond with an alkyl chain. So that's what we call alkylation. So the first step is to create that cation. In this case, it's going to be a carbocation. It's going to be a cation on carbon. And so we're going to use this catalyst for that, what we call aluminum chloride. So in this case, the aluminum chloride would react with this bond to give this our carbocation, and we'll end up with our carbon-carbon bond, our new carbon-carbon bond. Plus HCl, plus will regenerate our catalyst. Okay, so how does that work? Well, the first step is creating that cation. Okay, so in the case of this, the aluminum chloride is acting as a Lewis base again, okay, and generating a complex where we have the 4 chlorines around the aluminum and the carbon chlorine bond starts to break, and then we have an ion pair. We have a carbocation, a positive charge on carbon, plus the counterbalancing ion here. Now notice each of these steps is reversible. Okay, so they can go back and forth just as much as they want to. Sorry. Okay, but when we generate this, now we can have the electrons on that benzene ring reach out and form that new carbon-carbon bond. So when it does that, it again generates the positive charge. It moves around the ring until something acts as a base. And in this case, it's that aluminum tetrachloride acting as a base. And then that breaks down into HCl, regenerating your catalyst, and we have our new carbon-carbon bond. Okay, so when we have a carbon-carbon bond with just a regular sp3 hybridized carbon, we call that Friedel-Crafts alkylation. Okay, so there's a couple limitations with the Friedel-Crafts alkylation. Okay, the first thing is you can only do it with stable carbocations, which means you can only make a secondary or tertiary carbocation. So you're not going to be able to have something like, you're not going to be able to make a benzene ring with a long straight chain on it, because you can never form the primary carbocation that would be necessary to do that. But we can always get a secondary or a tertiary carbocation to form. So you'll never see a primary carbocation formed from that. The other thing that happens is that if there's anything on the ring that pulls electron density away from that ring, it won't work. Okay, so when we think about things that pull electron density away from the ring, look for partially positive charges, like in the case of this carbonyl. We have a partially positive charge and a partially negative charge on that carbon-oxygen double bond, okay? Because there's that partially positive charge, it pulls electrons away from the ring and it makes the reaction not work, okay? Now, that's true for all of these species with the carbonyl here. The other thing we have is when we have a sulfur or the carbon here or a nitro group, If we drew formal charges on there, we would see that we have partially positive or positive charges on these units. And when we have positive charges on that, it acts as a strong electronic drawing group. Okay. The other electronic drawing group we have is by induction. If we have a carbon with a lot of electronegative atoms on it, like that CF3 or that CF4. So think anything that's pulling electrons away from the benzene ring makes the Friedel-Crafts alkylation not work. Okay, so the next thing we have is we're still going to form a carbon-carbon bond, but it must be formed with a carbon-oxygen double bonded carbon. So it has to be a carbonyl carbon. Okay. Now, the reason this is because we already have a partially positive carbon here, and so it's easier to make the complex, and they are more reactive. Okay. So we're going to use the exact same catalyst, aluminum tetrachloride, and we typically use an acid halide or a carbonyl, carbon oxygen double bond with a chlorine, or it's almost always chlorine. So we replace that, the OH from a carboxylic acid with a chlorine, and that makes it very easy to form this complex. Okay. And when we do that, we always end up with a ketone. Notice here, we end up with a ketone. In the alkylation, we have just an alkyl group. In the acylation, we always end up with a ketone. Okay. So again, the mechanism is quite simple. We do exactly the same steps here. In this case here, we're using aluminum as our Lewis acid, our chlorine, and then transferred it to create our intermediate ion pair, where we have our aluminum tetrachloride and our acylium ion, which is a positively charged carbonyl, okay, or acylium ion. Okay. So notice that's the same steps as we used before. And notice they're all reversible. But once we get to this carbocation, the carbocation is very reactive, and of course reacts with the benzene ring, and then it liberates a hydrogen, regenerating the catalyst, and we have our ketones. We always have ketones from that. Okay. So, so it doesn't matter what acid chloride you use. For example, if you were to use a acid chloride with a benzene ring on it here, you would end up with a ketone with a benzene ring on it like that. Right here. So alkylations, alkyl group, acylations, always a ketone. Now, is there a way to form our primary, or a way to form our alkylations without having to use the aluminum chloride? Well, yes, you can. Any way that you can form a carbocation, you can use it to make an alkylation without having to use that aluminum chloride. So in the case of an alkene, right here, if we put a hydrogen on one side of this double bond, it would generate a carbocation on the other side. And remember, the hydrogen's always added to the side with the most hydrogens because it gives us our more stable carbocation. So it's going to give us our carbocation here. So just using acid as a catalyst, we can get an alkene to react with benzene to create an alkylation. Okay. Questions on that? Okay. So there's another way to generate a carbocation. What we saw when we take an acid with an alcohol, we can then protonate the alcohol here, and that acts as a leaving group, giving us our tertiary carbocation. So we can actually use an alcohol if we have a strong acid like H2SO4, sulfuric acid, or H3PO4, which is our phosphoric acid. So, but notice it's the same thing we're doing every time. We're generating a carbocation, and the carbocation is the reactive species in each of these reactions. Okay, so we know how to put a bunch of different things on. We can put a chlorine, a bromine, a nitro, a sulfur, which is the same mechanism as the nitro, an alkyl group, and we can make a ketone, okay? So that was just with benzene. But now we have to think of, okay, we already have something on there. What if we put something else on there? Okay, so the problem with that is whatever group is already on there is going to determine where it's going to add to your benzene ring, our orientation, and the rate at which it's going to add. Certain groups will make it easier to react with these cationic species. Certain things will make it not react with these cationic species. So we have to be very careful about what's on the ring because it's going to change where it attaches and how fast it attaches. Okay, so let's talk about the first one as this one right here, this OME, which as a group, it's just a methyl ether right here. And of course, if you remember, that has a special name. It's called anisole. Okay. Now, in the case of using our mechanism here, we're going to brominate it right here. And we're going to use acetic acid to generate that polarization to give us our positively charged bromine instead. Because this is very easy to brominate in the system. Now, if we just added the bromine to it and looked at the products we got, we would see we get products at two different locations. We get some of it at this 2 position, or 1 off of the substitution position, and most of it at this 4 position, and none of it in this other position here. So because we named it for this, this is our 1 position, 2 position, 3 position, and 4 position. Okay, so we get substitution at 2 and we get substitution at 4, but none at 3. There's got to be a reason for this, right? Well, the reason is that, remember when we had the species react with the benzene ring, we formed a positive charge, and that positive charge moved around the ring. Okay, so we have to stabilize where that positive charge is to do it. So when we have something like this that directs it in this 2 position, which is also the ortho position, and the 4 position, which is the para position, we call it an ortho para director, meaning the only places it's going to react is in that 2 ortho position and the 4 para position. Okay. In contrast, the nitro group is a meta director. Okay, it only reacts at that 3 position. Okay, so most of the time. So 93% of it reacts at this meta position, and only a little bit forms at that para and the ortho position. Okay. The nitro group is a very strong nitrator and can actually nitrate at those sites that are not directly activated. So nitro group is a meta directing group. So it only goes to this meta position. And so these are such minor products, we just say they're just impurities. Okay. So we have something that gives us ortho and para, the 2 and 4, and we have something that gives us the 3. So there has to be a common theme on why, right? Okay. And so the common theme is that anything that is electron donating in one way or another is what we're going to call ortho-para directing. So when I say electron donating, we're looking for things that have lone pairs directly attached to the ring, or have some kind of, a carbon-carbon bond on them. Okay, so let's look at this first set right here. So if we have a strongly activating system, that's things with a lone pair on it, like these amines right here, the phenol group, or this ether group here. Notice there's a lone pair right next to the ring. That lone pair can be donated into the ring to make the more electron density, and more electron density means it's easier for it to reach out and grab that electrophile. Okay, these are moderately, because notice we still have that lone pair, but we have a carbonyl next to them. That carbonyl is partially positive. So some of the electron density is being pulled to the carbonyl, and the rest of it's going to the benzene ring. So it activates it, it directs it ortho-para, but it's not as strong because of this carbonyl group here. Then we have what we call weakly activating. The benzene ring, it can donate a little bit of electron density from it. The carbon here can donate a little bit of electron density to it. So it's weakly activating, but since they have about the same electronegativity, it's not a lot. Okay. And then we have fluorine, bromine, chlorine, and iodine. And we call them weakly deactivating. because they're all more electronegative. They're all having a polar bond, pulling electron density into there, but they're orthoparadirectors. Why are they orthoparadirectors? Okay, they're orthoparadirectors because they have lone pairs. They all have lone pairs, and these lone pairs can contribute to stabilizing that charge. Notice everything with lone pairs is an orthoparadirector. Okay, so that's a really good indication as to whether you're going to be an orthoparadirector. And then how much electron density you can dump into the ring tells you how strong an activator it is. So it can donate all of this lone pair, some of this lone pair, doesn't have a lone pair, and then these are deactivating because inductively they're pulling electrons away, but the lone pairs can go back a little bit. So that's how you can look for orthoparadirectors. Okay. On the other hand, things that are going to metadirect are going to be things that pull electron density away from the ring. Okay, so we're pulling electron density away from the ring. So that means things that have carbonyls. Notice all of these with a carbonyl directly attached to the ring, because of that partially positive charge on carbon, it's pulling electron density away from the ring and deactivates the ring. Okay. It deactivates the ring, but it's still reactive, and it directs in that meta position. Okay. Now, if we look for strong deactivators, we have these. This is a full positive charge. If we did formal charges, that's a full positive charge on nitrogen. And on these, we have 3 very strong electron withdrawing groups. Okay. So those are strongly deactivating because they're pulling electron density out of the ring. When you pull electron density out of the ring, it's less likely to reach out and grab your electrophile. Okay, so do we see the common thing between orthoparadirecting and metadirecting? And we see that having that lone pair be able to donate that entire lone pair makes it strongly activating. Some of that lone pair weakly activating, moderately activating. How carbon bonds are weakly activating, and how the halides deactivate but still orthoparadirects. All right, so we have some generalization there. So alkyl groups, phenyl groups, and other substituents bond to the ring, and anything with a lone pair is going to be orthodirecting. Okay. All other substituents are going to be metadirecting. All of the orthoparadirectors are activating to some extent, except for the halogens, but they still are more reactive than the metadirectors. Okay. All metadirectors either carry a partial or full positive charge on the atom bonded to the ring. Okay, so what does that mean? That means that if you want a specific isomer and you have 2 steps to make it, you need to pick the correct order of those reactants. Let's say, for example, you wanted to have this isomer of nitrobenzoic acid. So we want the meta director, 1, 2, 3, right here. So that means we need to have something on the ring to put the nitro group in that meta position. So we needed to have something with a partially positive charge. And in this case, if we redraw this with our carbonyl here and our OH there, we have a carbonyl bonded directly to the ring. So that would make it an meta director. And that meta director would put the nitro group in that meta position, which means we have to start with toluene here and then oxidize it down to a carboxylic acid. Notice this is the same oxidant we use when we try to do make aldehydes and ketones, or ketones in particular. So it's the same kind of oxidant to make those ketones. Okay. But what if you said, well, I just want to do it the other way just for fun? Okay. Well, with the methyl group here, that's weakly activating, but it's also an orthoparadirector, which means if we tried to nitrate it first, we would end with the nitro group mostly in that para position. And then when we oxidize down our methyl group to our carboxylic acid, we would end up with the wrong isomer. Okay. So this is why orientation of the group is very important, and whether or not it's an orthoparadirector or a meta director. You can choose which isomer you want by keeping those in mind. Okay, so the why it works is what I'm going to talk about now. Why are some things orthometa directors, orthopara directors, but notice they all had some kind of donation of electrons. Okay, and all the meta directors had some kind of partially positive charge or full positive charge. That means that that positive charge that goes around the ring is going to play a major role in those directing effects. Okay, is that positive charge stabilized by electron donation? Then it directs it one place. If it is not stabilized by electron donation, it's going to show up somewhere else. And let's take a look at that. Okay. So we should have, there we go. Okay. So let's start with this anisole, right? So let's prove to ourselves it's uh, um, an activator and an orthopara director. Okay. It has lone pairs on it. Lone pairs means it's an orthopara director. Okay. But what if we, for some reason, attacked it meta? What would happen? Okay. If we attacked it meta, we would end up with a positive charge being on one of the either or one of the carbons next to where it was. And then we would be able to have it move around that ring. Okay. So we have the positive charge moving around the ring. And we have 3 contributing resonance structures to this. Okay. And then the fast step, again, would be to lose the proton and get our product here. Okay, so that doesn't seem too bad. Our mechanism started with 3 resonance contributors, so we're not hurting anything here, right? Okay. Well, what if we attacked at the ortho or para? I'm going to start with the para first. So we said this is an activator, and we said it was an ortho-para director. Okay, but let's prove to ourselves why that happens. If we attacked in that para position, we again would have the positive charge on either side of where it attacked. It would move around the ring, so it'd go over here. And notice that because we have a lone pair here, we can move the positive charge out of the ring onto that oxygen atom. Okay, so we had 3 contributing resonance structures in the previous one. Now we have 4 contributing resonance structures. Okay, if we have 4 contributing resonance structures, that must be more stable. And because it's more stable, it's going to be more favored. And therefore, it's more favored because of that extra resonance structure where we can stabilize that positive charge using that lone pair on the ortho-para director. Okay. And of course, the last step is losing the proton. Okay. So let's try that with the nitro group and see what's happening here. So let's do that meta attack first again. We know nitro group because it has a, when we draw our Lewis dot structure, our formal charge of 1 on nitrogen and -1 on oxygen here. So we have a full positive charge on that nitrogen. And let's say we attack there. And so, of course, we're going to create a positive charge on either side of that nitro group. And then it can move around the ring, giving us our 3rd resonance contributor. Okay. So, okay, 3 resonance contributors. That's about the same as before, right? And so then, of course, our fast step, we lose the hydrogen and we generate our meta compound here. Okay. So notice that we have a positive charge on nitrogen here, but it doesn't interfere with any of those positive charges moving around the ring. What if we attacked in a different position? Let's attack para. Okay. So let's do that para attack here. And what's going to happen is, of course, we're going to get our resonance structure with our positive charge on either side first. But now, when we try to move that positive charge to this position here, we'll have a positive charge next to a positive charge. Okay. Okay. A positive charge next to a positive charge that doesn't want to have 2 positive charges next to each other. So that's going to be a very, very disfavored configuration or very unlikely resonance structure. So you can almost cross that out as a possible resonance structure, giving you 2 resonance structures. Okay. So that means that that ortho-para direction, well, it can happen. It only has 2 resonance structures, making it less likely to happen and go to our products here. Okay, so in the case of meta attack of an activator, we have 3 resonance contributing structures. In the case of ortho or pair attack on an activator, we have 4 resonance structures capable. So those 4 resonance structures are what's favored, and therefore it's going to be an ortho para director. When we have a meta director, when it attacks meta, we have 3 resonance contributing structures. When it attacks ortho or para, we only have 2, making it the disfavored product string. This is why we have ortho and para direction based on whether it's an activator or a deactivator, or one of those like halogens, which has that lone pair to contribute. Okay, questions on ortho para direction? Okay, so this kind of summarizes that. There are resonance effects where we can pull those electrons in, and then there are inductive effects. Okay, the inductive effects are saying we are withdrawing electron density from our system, and therefore it deactivates the ring and is a meta director. If we have lone pairs to contribute, it can help delocalize the positive charge on that atom off the ring, giving us an extra resonance structure, and gives extra electron density to allow it to have a lower activation energy to reach out and grab our structure. Okay, now I said halogens are deactivators, but orthopara directors, and this is why. Okay, inductively, right here, it's pulling electron density away from the ring. Okay, but when the positive charge resides on that atom that the chlorine is bonded to here, it can donate electron density and it stabilizes the positive charge off the ring. So by resonance structure, it has a 4th resonance contributor, making it an orthopara director. Okay, but inductively, it's not putting electron density into the ring, therefore it deactivates it slightly. So it's the only one that does both. So make sure that you keep track of that. Okay. Now, once you have more than one OH group on a phenol, we start getting a little bit in trouble of trying to look at how and where that works. So in just a simple OH on the ring, we call that phenol, phenyl alcohol, phenol. But when we add a methyl group to it right here, we change the name, and we should be changing the reactivity because now we have 2 different orthopara directors. Okay. If we have 2 OHs on there, we call that catechol. If they're in the ortho position, if we have 2 and they're in the meta, we call that resorcinol. And if we have 2, but in the para, we call that hydroquinone. Okay. And the cool thing is, even though they are all very similar, in looking like that, they all have very different reactivities. So, and phenols are actually used extensively in things like flavorants and things that react with the body. So things like thymol, which is, I want to say it's a flavorant used in several things, and vanillin, which is also a flavorant with an aldehyde group on here. These are all naturally occurring in the body and can be used, and they use those OH groups to help solubilize them in water. And we can even have long chains hanging off it. This is hexylresorcinol. This is eugenol. It's actually used as a, it has the methoxy and the OH on it, and I've never actually found that, but I think that's a natural odorant in in certain plants. I forgot. I'll have to look that one up. Okay, so when we have that OH there, we have to think, okay, does it hydrogen bond? Because it's got an oxygen and a hydrogen, so it probably hydrogen bonds. And if it hydrogen bonds, it probably also is acidic. Okay, So if we look at the pK of phenol, we found that on that table when we did our acids and bases, phenol was the most acidic alcohol-like species. Okay, ethanol was just above water, right around 16, but phenol was below water, right around 10. Okay, the reason we can do that is it has everything to do with the benzene ring being able to stabilize that negative charge. Remember, things that have a delocalized negative charge are more acidic. Let's see, do I have a, yeah, I do, good. So if we deprotonate our phenol, we're going to end up with an anion right here. But then through electrons, through pushing electrons, we can actually put the negative charge on the ring. Then, of course, that pushes it 2 carbons over, puts the negative charge on the ring, and then pushes 2 electrons over more. So we have 3 different contributors, resonance contributors, that allows that negative charge to be spread out over 4 different atoms. We have it just on the oxygen, and then we have it spread out over the ring. So just like an acid-base system, that is where we get our greater acidity with phenols than with the alkoxides. Remember, the alcohols, the negative charge is on that oxygen, it doesn't move around. The negative charge on a carboxylic acid can move back and forth by resonance between 2 atoms, 2 oxygen atoms. And that's what makes it more acidic. In the case of phenol, we're moving that negative charge around the ring. Okay. So if we're moving the negative charge around the ring, that means that by adding an electron donating or electron withdrawing group, it's going to change the acidity. Okay. So if we have a group that is going to donate electron density, it's actually going to decrease the acid strength because we're trying to move a negative charge. And if we're trying to donate extra electrons with a negative charge, it's not going to help. But if we put something that is an electron withdrawing group, like chlorine is inductively electron withdrawing, and the nitro group is electron withdrawing, it gets more acidic, okay? Because we have a positive charge on the nitrogen here. When we move the negative charge to here, it is stabilized. We have a positive next to a negative. They're balancing each other out. That makes it more acidic. So the introduction of electron withdrawing groups, either by resonance or inductive effects, will give it a stronger, a more stable anion, which gives us a stronger acid. Questions on that? Okay, here we go. Okay. But, you know, so phenols are weak acids, but they're stronger acids than alcohols, okay? And so we can use that to our advantage because when we use a very strong base, we can actually use sodium hydroxide to deprotonate that phenol. We can't do that with regular alcohols very readily because the OH is the alkoxide is a stronger base than the OH is. But because the phenol is more acidic than a regular alcohol, we can deprotonate it with our thing. And if we note that the pKa of the acid on this side is 9, and the pKa of water, which is formed, is 15.7. 9 is more acidic than 15.7, so this is the weaker acid, so the reaction progresses forward. Okay, but they don't react with weaker bases, okay? So we can have something like a sodium bicarb, which would create carbonic acid as its conjugate acid. Carbonic acid has a pKa of a little bit above that of acetic acid at 6.37. And so when we have it, the phenol is around 10. So what we have is most of it is going to be in here, but they're close enough together that a little bit will be deprotonated, but the reaction equilibrium will lie to the phenol. Okay. So we can use that to our advantage, okay? Because regular alcohols do not deprotonate with sodium hydroxide, but phenols are acidic enough to deprotonate with that. So if we had a mixture of 2 components, this is just cyclohexanol. So that's going to have a pKa of above water, so it's going to be above 15.7. And we have our chlorophenol right here. I'm sorry, our methylphenol here. It has a pK around 10 because it's down in the phenol range, okay? So that when we take it and extract it with our sodium hydroxide, only the phenol is going to be deprotonated. The OH is going to not be deprotonated and stay in the non-aqueous layer, stay in the organic solvent layer, because there's no reason for it to go into water. It's 6 carbons, it hydrogen bonds a little bit, but mostly the 6 carbons controls its solubility. So that means is if we remove the ether, we're going to end up with pure cyclohexanol. But if we take that aqueous phase, because we deprotonated this, making it more soluble in water, we can then add acid to the system and get it to come out, and we will have isolated our phenol. So we're using the acidity of phenol to help separate the material from other alcohols. Okay. So the other cool thing that phenols do is they are used as antioxidants. Okay. So you know there's a lot of the phenolic materials are actually highly colored materials, like some of the colors in blueberries and stuff that people think, oh, these are great antioxidants. Well, what does that mean? What it means is they can react with oxidizing species to generate stable systems, and they react more readily than other things. So in the case of phenol, it just sitting around in air, it can react with itself to convert it into, it can react with oxygen to create other compounds. In the case of oxygen just reacting with stuff, it can actually do a radical reaction where it can create what we call peroxides right here. So this is called a hydroperoxide, but if you also put it on a chain, it can be a peroxide. So when we have oxygen, it'll react with double bonds, it will react with the carbon next to double bonds, it'll react with anything with an activated hydrogen and create these peroxides. Now, technically, peroxides are typically very bad because they, number one, in high concentrations become explosive, they're very reactive, they are thermally unstable. But it's just a natural process in air. So what we can do is instead of that, we can actually use phenols as an antioxidant to keep them from happening. Okay. So in the case of this, we're actually going to use, why are we using that? Okay, that's in the wrong section. That should be something else. Okay, so phenols as antioxidants. So several things we use naturally as antioxidants have phenolic groups in them. For example, vitamin E here, which has, this is actually a much longer chain. Notice there's 3 there. We'll talk about polymers in chapter 16. The ability for it to oxidize and form a double bond here is the reason it's a natural antioxidant. It will react with oxygen, it will scrub those oxidizers like the free radicals by reacting with the species here. These are also synthetic ones that are found a lot in food and also in cosmetic products. And it's basically other derivatives of phenol such that they are less soluble in water so that they can be used in our liquids and oils. And so they can act as antioxidants in oils by using this to create our double bonded system here and scrub all the oxidizers and the free radicals out of our system. And that is the end of chapter 9. Any more questions about chapter 9? Oh, I should leave that. Am I muted? No? There we go. Okay, so what I'm going to do is I'm going to go ahead and start chapter 10, and I'm going to use those goal slides that I was talking about there for our remaining amount of time. Here. So chapter 10 is amines, okay? And so amines are another derivative of what we have, but it's named for the nitrogen group being bonded to a carbon. And so we're going to talk about that. So our first goal here is to talk about nomenclature and how it bonds, okay? So this is a new functional group. We talked about it when we did nomenclature, but let's go ahead and go to it again. So unlike carbons and alcohols, amines are classified by how many carbon-nitrogen bonds there are, okay? So if we have no carbon-nitrogen bonds, it's technically an inorganic compound called ammonia. If we put one carbon bond to it and two hydrogens bonded to the nitrogen, we call that a primary amine because there's one carbon attached to it, okay? If we have two carbons attached to it, we'll call that a secondary amine. And if we have three carbons attached to it, we have a tertiary amine, okay? So we have to think about what they are. So how many carbons are attached to it gives us the classification. Notice that the first one, the ammonia and the primary and secondary still have a hydrogen on them that can hydrogen bond, okay? So pay attention to that. The tertiary does not have a hydrogen, so it itself doesn't hydrogen bond, but it has a lone pair that you can hydrogen bond to, okay? Okay. All right, so then we can actually, there we go. So we can further break that down into things that only have alkyl groups on them or things that have aromatic groups on them. And remember, when we had an amine and an aromatic ring, we changed our name. We changed it to aniline, okay? So if we have just aliphatic groups, it's an aliphatic amine. If we have a benzene ring attached to it, one or more, we call those aromatic amines. Okay. So those are different classifications and they have different amounts of acidity and basicity. Okay. In the next class we have are what we call heterocyclic amines. We have two types. We have heterocyclic aliphatic amines, which means no double bonds. It's not aromatic. It can have double bonds, but it can't be aromatic. So those are rings containing nitrogen, but are not aromatic, don't meet the rules of aromaticity. But then we also have heterocyclic aromatic amines, things that meet the rules of aromaticity. So in the case of this one right here, we have 1, 2, 3, 4, 5, 6 electrons in a ring, flat, all pi electrons, all p orbitals. So it is an aromatic ring. Okay. And they each have different properties, the aliphatics, the aromatics, the heterocyclic, and the heterocyclic aromatics. So let's kind of classify each of these as a primary, secondary, tertiary, aromatic, aliphatic, etc. Okay, so let's start with this first one here. Okay, so what do we think? Is it primary, secondary, or tertiary? Okay, chat's open.
Secondary?
Secondary, because we have two bonds to carbon here. So we're going to start with a secondary. Is it an aromatic amine or an heterocyclic aromatic amine? I don't see any aromatic rings attached to the nitrogen, so it's not one of those. However, it isn't a ring. So we're going to call this a heterocyclic secondary amine. So we have a cycle with nitrogen in it, we have a circle with nitrogen in it, we have a secondary. So it's a secondary heterocyclic amine. Okay. So using that same kind of argument here, we have two different types of amines. Okay, let's take this first pronoun here. What do we have here? Primary, secondary, tertiary?
Tertiary?
Tertiary, because we have three different bonds to carbon. So we have a tertiary heterocyclic amine. Okay, let's look at this side over here. What's this? It's not primary or secondary because it's got, well, I guess technically you could call it tertiary because it has, or secondary because it has 3 carbon bonds. But what else? Was there a special name for it?
Aromatic.
Heterocyclic aromatic amine. Yeah. So notice that it's in a ring and it can be aromatic. Okay. And let's just go for this one right here. Now, because the benzene ring is way over here, it's not an aromatic amine. So that means it's just it's an aliphatic amine, but it's a special kind of aliphatic amine. So it's in a ring, so it's a heterocycle, and it has 1, 2, 3 bonds to carbons, so it's a tertiary heterocyclic amine. Okay, so we need to make sure we can classify each of these types as aliphatic aromatic amines, heterocyclic aliphatic amines, heterocyclic aromatic amines. Okay, so when we name aliphatic amines, we just basically name the R group that's on there. If you have one R group, you have just name that whatever that regular group here. In this case here, we have a butane, and it's hooked to the secondary carbon, so that's 2-butane amine. Okay. Here we have a phenyl group, but the amine is not directly attached to the ring. So it didn't change the name of that phenyl group. So the phenyl group is a substituent, and we name for the longest carbon chain. So we have 1, 2 carbons here. So we have ethylamine or ethamine, okay? And we put the phenyl group as a substituent, okay? Now here we do have a wedge here showing us we have chirality, okay? And if you have more than one amine on a long chain, you would just identify it as where the different amines are and a diamine or triamine. So you can have a 1,3,5 hexane triamine. In this case here, we have 1 at each end, and so it's 1,6 hexane diamine. So it's similar to the alcohols that we have. It's just, it is a little different. Okay. In our U-Pack names, when we have the ring, we learned this in the last chapter, when we have the amine on that benzene ring, we call it aniline. And if aniline is the highest priority group there, everything is named for it. And we start with aniline with 1 always starts where we're naming that ring. And so we have the 4-nitro aniline, the 4-methyl aniline, and in this case, the 3-methoxy aniline. Now they all have special names. This is toluidine and acinidine, but the IUPAC name is always correct. So don't worry about the special names here. Okay, so if you have more functional groups than just the amine, remember amine is one of the lowest priority groups. So if you have anything like an alcohol or higher, it's going to be named for that. So in the case of having this being 2 carbons and having an ethanol, the amine is a substituent, and so you identify its location and call it amino as a substituent. And so we have 2-amino ethanol. And in this case here, we have it on the 1, 2. This is benzoic acid. And so we have 2-amino benzoic acid. Because of that low priority, unless that's the only functional group there, it's typically named for the other functional group. Okay. So when we look at common names, we just talk about what the alkyl group is and tack the word amine at the end. So if you have one group on there and it's a methyl group, we would just call it methylamine right here. In this case, we have a T-butyl group, so it's T-butylamine. If you have more than one group, you name each of them, okay? So in this case, we have a cyclopentyl group here. We have a second cyclopentyl group here. So we have dicyclopentylamine. And 3 of the same groups, we're gonna just name it the triethylamine. If you have multiple groups that are not the same, you have to put them in alphabetical order. So you had methyl ethyl butyl amine, you would do butyl ethyl methyl amine. Okay. Now, if your amine reacts with an acid or reacts with another alkyl group to generate a positively charged nitrogen there, so you have 4 bonds to nitrogen and a positive charge on nitrogen, we've now changed them to an ammonium ion, okay? So in the case of an ammonium ion here, you would name the groups. We have the trimethyl ammonium and then whatever the counter ion is. Here, when we have the heterocycle here, we would have that heterocycle as the ion. So in this case, it's the pyridinium ion right here. In the fourth group, the fourth attachment to carbon is this hexadecyl group here, and then the counter ion. And here we have, this is a benzyl group, so it's not changing it. So we have a benzyl trimethyl ammonium, and then our counter ion is hydroxide. So whenever you see a salt, look for an inium at the end. If it's not an aromatic ring, it'll typically be ammonium. If it is an aromatic ring, then it's going to be named for that aromatic ring. Okay. So when we talk about hydrogen bonding, amines are, nitrogen is one step over from oxygen. So oxygen is more electronegative than nitrogen is, okay? And therefore, the bond difference between the nitrogen and hydrogen is a little bit less, okay? Because it's a little bit less, that means it's going to be a weaker hydrogen bonder. So there's going to be a greater effect in an alcohol in the boiling point and melting point than in the case of an amine, okay? So remember when we did alcohols that the OH was the strongest hydrogen bonder, and because the difference between sulfur and hydrogen was so low, it hardly hydrogen bonded at all. In the case here, nitrogen is intermediate at a 0.9, and therefore it does hydrogen bond, but it doesn't raise the boiling point as much. So in having similar molecular weights here, we actually have a 70-degree difference in boiling point, and that all has to do with the weaker hydrogen bond of the nitrogen. All right, questions on our goal number 1. So, nomenclature. 4 different classes plus 3 different types, primary, secondary, and tertiary. Okay, let's see. We're right here at 12 o'clock, so I'm going to go ahead and do goal 2, and that should close out our class today. So our second goal in here is basicity. Okay, now, when we did acids and bases, we focused mostly on the pKa's of things and the acidity of things. When we talk about amines, the fact that they are Lewis bases, that lone pair acts to pull hydrogens to it, we have to talk about the basicity of the system. And remember, the basicity is the opposite of acidity. Okay. So all amines are weak bases, and in aqueous solutions, they can act as bases to create a little bit of the ammonium salt and hydroxide, but it's reversible, okay? So all amines are going to have some equilibrium constant that gives us that, and if we take the natural log of this equilibrium constant, we'll get the Pkb, because we have a hydroxide concentration on the top here. Okay. So if pKa is the concentration of hydronium ion on top, pKa is the concentration of hydroxide on top. The cool thing is that if we add the pKa to the Pkb, we always get 14. So that means we can have an acidity constant and actually convert it into our basicity constant just by using this agreement here, which means your Pkb is going to be equal to 14 minus pKa. Okay, that's B, and that's A. Okay, so what is this? Why do I say this? Well, it helps us understand that when we talk about amines, we almost always talk about basicity, and knowing that how to convert the pKa to the Pkb is useful. Okay. Now we can use, again, when we did those acid-base reactions, we always looked at just the pKa of the acid or the conjugate acid. So let's look into that next to see which direction the equilibrium will lie in these reactions. Okay, so if we just had methylamine right here, and we know that's a Lewis base, we have a lone pair here, We have acetic acid. It has a hydrogen that it can give up, so it's the acid. And we mix them together in a solvent, and we want to see which direction this lies. Well, we do what we did before. We compare the pKa on the one side of the reaction to the pK on the other side of the reaction, and we see that the protonated methylamine here has a pKa of 10.64, which makes it the weaker acid compared to the acetic acid, which means the equilibrium formula is going to lie in this direction. So we're still going to have both of these, but we're going to have more of these, a higher concentration of these, because remember, we always want to go from strongest to weakest in the acid system. I don't know why I'm coughing so much here. So let's now change our minds and think about Pkbs. Okay, so we were thinking about basicity. And just like pKa's, the lower the number, the stronger the base. Okay. Okay, so let's look at these. If we look at ammonia itself, it has a Pkb of around 4.74. Okay, so it is kind of basic, but it's not a strong base because those would be negative numbers. So it's a weak base, but it's a base. Okay. If we add an alkyl group to it here, it actually becomes slightly more basic. Okay. It has a carbon to pull electron density from and donate electron density to it. So it becomes a slightly stronger base, but they're still weak bases because they're in the 3 range. They're not below 0, but they are stronger than if it had no carbon at all. Secondary amines actually are about the same, and then tertiary amines are a little bit less basic most of the time. Okay, so it's again the lone pair on all of these is the thing that's doing the base. Now, once we get to the aromatic systems, things change a little bit. Aniline itself is much more basic, less basic. It's a higher number, it's less basic than the system here. And that has the idea that it can share electron density with this ring here, making it less likely to act as a base, less likely to protonate this species. Okay. So if electron density is making it less basic, that means by changing the groups on there, put an electron drawing group or electron donating group, we should be able to change that basicity. So if we have a slight electron donator group on here, donating electron density here, less of it's being pulled away, and it is actually a stronger base. It's a stronger base because it has less electron density being dumped into the ring because of our donator. But if we have electron drawing groups, that's pulling more electron density, it should become less basic. So we'll see the numbers jump actually up because of those electronic drawing groups. They're making it less basic because it's pulling electrons away that would be for the lone pairs here are being pulled into the benzene ring and therefore are less available to act as a base. So it decreases the basicity. Now, when we're sharing some of these electrons, we have to be careful because in this case here, we have a lone pair right here. So that lone pair is actually not shared with the benzene ring. It's in a separate orbital. And that actually increases and makes it into a weak base, but it's stronger than some of the other ones. It's a stronger base than aniline itself, but it's not as strong as an aliphatic amine. In the case of imidazole, we again have a heterocycle. You think, oh, that looks like an aliphatic amine. Well, no, it's actually in the conjugated ring, and therefore it has it's a weaker base than the aliphatics, but it's a little bit stronger than the aromatics. Okay. All right, questions on the basicity of different materials. The aliphatics are much stronger bases than the aromatics, and the heterocyclics are kind of intermediate. Okay. So if we have the difference in the aliphatic and the aromatic, we can use that to help us separate them, okay? Aromatic amines are much weaker bases than the aliphatic, and so that we'll see a much bigger difference in the pKa. In the case of cyclohexane, we have a Pkb of about 3.34. Notice that's a whole 6 points difference than with aniline. Okay. So because of that, and the reason that they're less basic is because they can donate part of the electron density of their lone pair to the ring, and it'll move around the ring, making this less likely to reach out and grab protons. If we look at the aliphatic one here, there's nowhere for these electrons to go. Those electrons will only act as a base. They will not delocalize around the ring, and therefore that's why it's a stronger base. And if we have those electronic drawing groups on there, we're actually encouraging more electron density to be pulled away, making it an even weaker base than it was without the electron withdrawal. Okay. So let's use those rules and figure out which of these is going to be, for part A here, which is the stronger base. The A, which is the pyridine, or B, which is a morphine. That's actually the name of it, but you don't need to know the name. Okay. Oh, cool. You can put your name on it. That's great. Yeah. And it's that because it's an aliphatic amine. B is the stronger base because it's an aliphatic amine. This is a heterocyclic aromatic amine, so it's a weaker base. Okay. All right, so let's make them both have benzene rings on this one here. Which is it going to be, A or B? I'm sorry, C or D? Chat room still open. Okay. So in this case, you might be tricked because, oh, there's a benzene ring, okay? But we have to look at where the amines attach. The amine is attached directly to the ring here, making it an aromatic amine. The amine is attached to this CH2, making it an aliphatic amine, which means this is going to be the stronger base of the pair. Okay, so this is a benzylamine. We have that CH2, that sp3 hybridized carbon, making it a stronger base. Okay, so can we increase the base strength a little bit? Well, we can make the strongest base among the organic compounds is what we call guanidine. Okay, and the reason it's stronger is because it can delocalize the positive charge out over three different nitrogen atoms because of resonance structures. Okay, because of resonance delocalization of that positive charge, it's more likely to accept a proton, and then so each of the nitrogens only shares a third of that positive charge, making it more basic. It's just like the opposite of the acetic acid. The fact that you can share that negative charge over 2 makes it more acidic than other oxygen-containing acids. Because we have 3 nitrogens here and we're sharing that charge, it is the most basic of the sets. Okay, and that is all I have for goal 2. Okay, I will stop here and pick up with amines goal 3, the reactions, on Tuesday. So I'm going to go ahead and stop recording. And